Okay, so in the second part, we'll talk about symmetric group, but first I want to start with talking about equivalence relations. Equivalence relations, and I hope almost all of you know what an equivalence relation is, but I will briefly remind you because I actually need that a lot in this course, and also we'll go through several examples related to groups which appear a lot, and we'll need it soon for symmetric group. Okay, so let me just remind you, this is a very general nonsense in set theory. So definition. So if A is a set, a relation R is just a subset in A times A. So just some pairs are in the relation. And you might ask, what is the big difference between a relation and this oriented graph with loops, which I explained last time? And honestly, I don't see any. But this probably is a little bit different way to think about it. And then there is a property, that's a definition, there is a property. So R is an equivalence relation if the following three axioms are satisfied. So for every A in A, pair A, comma A is in R. So it means A is in the relationship R with A. Then this relation is symmetric. For any AB in A, AB is in R, then BA is in R. It means that basically if A is in this relation to B, then B is in the same relation with A. With its very nice property. Not always happens in life, but for equivalence relation we expect that. And for every ABC in A, if AB is in R, BC is in R, that implies that AC is in R. That's called transitivity. So let me kind of explain. So usually the notation is AB is in R. The notation is A is equivalent to B. Depending on the context, there will be different sign here. And you can say R inside. And so the last one, so this is A is equivalent to A. This symmetricity is A is equivalent to B if and only if B is equivalent to A. And the last one, A is equivalent to B is equivalent to C, then A is equivalent to C. And in intuition behind this equivalence relations is that it's some kind of a rough kind of idea of equality. So A and B are not like equal maybe, but they are in this equivalence relation. It means they are kind of equal if you look at them without too much precision. Like you can say that, for instance, two sets are equivalent if there is a bijection between them. And all properties will satisfy, and it means that kind of sets are not actually equal, but they are kind of the same. So examples. There are so many examples, and you know already probably quite a few of them. So examples are for instance, you can say, yeah, that starts to be a little bit complicated because I want to say that for instance isomorphism of group is, but if you just look at all groups, they don't form a set. That's kind of set theory issues. So kind of, you probably know that set of all sets doesn't exist. It's self-contradicting notion. You can look at all sets which are not elements of themselves, and then you have got into trouble. And the same is true for groups. So you cannot say just set of all, like isomorphism is equivalence relations on groups, though it satisfies three properties, because groups don't form a set. But let's ignore it. So I mean, so if G, so isomorphism is an equivalence relation relation, but again, like up to this issue that groups don't form a set. So, I mean, you can say finite groups, you can say countable groups, you can say like anything like that, or you can say groups which are subgroups somewhere. Just whenever you have any set of groups, then it will be an equivalence relation, or you can just say, you know, these three properties are satisfied. And this is something which already appeared in this exercises when we discussed isomorphism. And the reason was that if you want to show, for instance, the last one, you look at group 1, which is isomorphic to G2. So G1 is isomorphic to G2, implies that there exists this isomorphism F. And G2 is isomorphic to G3, implies that there exists this isomorphism from G2 to G3. And then you can just do composition. So G, and then you can take G1 to G3, which is first you do F and then you do G, and this will this is an isomorphism, so we get isomorphism between G1 and G3. Similarly with first two. So and it means that isomorphism is a meaningful kind of way to say two groups are equal if they are isomorphic. These three properties are satisfied. Okay, so we'll go to another examples, but before that, there is a fundamental idea of factor set. So factor set, if you don't like this word, factor set, because it looks too fancy, you cannot use it. I mean, I don't use it honestly, but we'll see factor groups, and maybe some of you have seen factor vector spaces, factor rings. So you'll see a lot of factor something, and this is a general construction. So if you have this thing is equivalence relation on A, one can form a new set, which is denoted A factored over the relation. So this will be called factor set. And this is set of classes of equivalence. So the idea is that you can identify equivalent elements and you will have smaller set where elements there are just classes of equivalence of elements. And a typical example is, for instance, we can call, I don't know, two people equivalent if they have the same name. And then if you take all people, a set of all people, and factor it over this equivalence relation, you will get a set of names. Because every name corresponds to a class of equivalent people with respect to this equivalence relation. Or you can take groups up to this equivalence relation being isomorphism, you will get groups up to isomorphism. For instance, the set of groups with one element, with two elements, for instance, is kind of absolutely crazy. You can take sort of any symmetry of anything and it's a group, and they are not equal, but they are isomorphic. And so set of isomorphism classes of groups with two elements has just one element, being this group Z or 2Z or S2, whatever you like. Okay, so let me remind you how this construction goes. So again, I hope you have seen this theorems proven. So definition is as follows. So you can look for X in A, let brackets X be a subset of A, and the subset consists of elements Y in A such that Y is equivalent to X. So you just look at all elements which are equivalent to X and you put this bracket for a subset. And then there is a fundamental lemma here, which is simple but important, is that so this thing is called equivalence class. Equivalence class. And the fundamental statement is two classes either not intersect or coincide. So if you have two classes, then either they are completely distinct, no common elements, or they actually are literally the same, no other options. So why it is so, imagine, so again, I expect you know this theorem. If not, you should look it up. But imagine two classes intersect. There is one element inside both of them. It's equivalent to X, it's equivalent to the element in the other class. By transitivity, this means that these two elements in these classes are equivalent. And so actually you have class generated by X and some other elements say Y, then X is equivalent to Y. But then you show any other element in the first class is equivalent to X, by transitivity it's equivalent to Y, so it's in the second class and vice versa. Classes are the same. So if they have one element in common, they just coincide. And like imagine we talk about people and names, we have two crowds of people, all people named Jane and all people named Albert, and these crowds are distinct. If there is a person in intersection, it has the same name as both of them, so the names coincide. That's as simple as that. So that's one statement. And then there is another statement. Let me erase now this part, and I will just continue. Okay, so there is another lemma. Is that every element in A lies in some class? And that's complete tautology, because just A lies in the class containing A. Nothing to prove here. And so I don't even prove it, I just kind of say it like that to have a clear structure. And then there is a corollary. So then we know that our set A is every element is inside one of the classes. They don't intersect. So A is a disjoint union of equivalence classes. So as simple as that. And the typical picture which people draw is that this is A, and then there is this classes of equivalence, and then there is a set of classes, this A, like let's call them 1, 2, 3, 4, 5, and then the set of factor set will contain just 5 elements kind of corresponding to names of these classes. Okay, so this is a very important general formalism. If you want, if you have a set and you know that there is some way to kind of divide elements in groups so that these groups don't intersect, according to some rule, you actually get equivalence relation. One can formulate a theorem, which I'm a little lazy to do, that actually if you have a presentation of your set as a union of not intersecting subsets, then you can define equivalence relation, where two elements are equivalent if they are in the same subset, and this is indeed an equivalence relation. So that's very straightforward. Okay, so I want to give you a few more examples. So examples. So we did already isomorphism. So here are two more. So example 2 will be very important. So we can take as A the set Z, and then we can take some n as just some integer, and then we say that A is congruent to B mod n if n divides A minus B. So this is just this relation called congruence. When I asked you in the questionnaire whether you know this theory of congruences, I meant that. And this is just the same as A and B have the same remainder mod n. So they have the same remainder when you divide them by n, and that's an equivalence relation, and that's really easy to see. So A is congruent to A because 0 is divided by any number. If A is congruent to B, B is congruent to A because you can just multiply by -1, and if A minus B was something times n, b minus a will be minus something times n. Finally, if a is congruent to b is congruent to c, you know a minus b is divisible by n, b minus c is divisible by n, you add them up, you get that a minus c is divisible by n. So it's an equivalence relation. And indeed, if you just take all integers, you can just divide them into these groups. So these are guys congruent to 0, to 1, and so on to n minus 1. And for instance, if you look at number n, it will be in the same class as 0 because n minus 0 is divisible by n. N plus 1 is here, 1 minus n is here, 1 minus 2n is here, 2n minus 1 is here, and minus 3n is here, and so on. So that's the typical picture. And if you denote these classes by 0, 1, and so on, n minus 1, you get that this factor set z over this congruence relation is exactly z over nz we discussed. And then there is a way to add these classes, but we'll come to that when we talk about cyclic groups in about a week. So that's a very important notion, equivalence relation on integers being congruence classes. So I want to discuss one more equivalence relation before coming to permutations, and this is the one related to conjugation. So you have seen this idea of conjugation when you learned about matrices and linear algebra, and I want to discuss it from group theory perspective. Okay. So, definition. So let G be a group. So then G1 and G2, of course these are elements of G, are conjugate. If there exists an element x in G such that G1 equals x, G2 x inverse, and we'll denote it G1 is congruent to G2. Okay, so notice this is very important. So this whole conjugation business comes in because group is not commutative. If you know that you can exchange the order of x and G2 without getting into trouble, you will get that x times x inverse is identity, and so G1 equals to G2, so there is nothing interesting going on. For abelian groups, conjugation doesn't exist. But for general groups, it very much exists, and this is an equivalence relation. So proposition, so conjugation, being conjugate is an equivalence relation. And that's really simple. So proof is that, okay, so there are three properties. The first one is, so G is conjugate to G, and the reason is because, and that's really simple, G equals to identity, G identity inverse. So that was the first property. So if G1 is congruent to G2, that means that there exists some x in my group such that G1 is equal to x, G2, x inverse. But then I can multiply on x inverse from the left and x on the right. That implies that x inverse G1 x equals to G2. So now it means that G2 is equal to x inverse G1 x inverse inverse. Because remember, double inverse is just x. So G2 is equivalent to G1. And finally, there is part 3. So this was part 1, part 2, and there's part 3. And part 3 is a very important exercise. So just this is a part which is called transitivity. So please look at that in some detail. That's very important. Okay, so what is all this for? So this conjugation is a very deep idea, and unfortunately right now it's hard for me to explain why it is so deep, but we'll talk about it when we talk about group actions and symmetries and so on in more detail. But let's just look at some examples. So if you take, so it's again an exercise, so another exercise. Maybe I will even put it in homework next time. So if you take S, oh no, I will not. So let's take S3, and I want to think of it as a symmetry group of a triangle. So there are 3 vertices, A, B, C, and I remind you the structure of this group. It has 6 elements, 3 of them are symmetries. There is identity, rotation by 120 degrees, which I just denote by R, and R squared. And then the claim is that, so one can look at this equivalence relation. And the claim is that there are 3 conjugacy classes. So, I mean, these are 6 elements, so I can draw my group. 1 second. So I can draw my group, and I can divide it into 3 classes. One will contain identity, the other will contain R and R squared, and the rest will contain the symmetry A, symmetry B, symmetry C. And that's really a simple exercise to check that this is true, but I mean, I can sort of do that. For instance, R equals to, I think, SA R squared SA inverse, and then if you do something like R SA R inverse will be, I don't remember, probably SB, maybe SC, and so on. So and R squared SA R inverse will be SC, maybe vice versa. And of course, the only element conjugate to identity is just identity. So there are 3 classes, and if you look at the picture, that makes sense, because, I mean, this has 3 different types of elements. Rotation, identity, which is very special, rotation by something, and symmetry with respect to a line. And notice 3 different symmetries for 3 different lines form the same conjugacy class. So if you want to name them, you will literally say identity, rotation, symmetry. That's not a coincidence. In general, this conjugacy classes has a meaning of kind of classifying elements in a group in types depending on what they do, roughly, and what is kind of their geometry behind them. And let me give you another example. So another example will be the one which is very familiar. So let's take as a group G, GLN of F, and I remind you, these are n by n. So these are this n by n invertible matrices. So no problem. So what is a conjugation classes? So A is conjugate to B if and only if there exists X such that A equals X, B, X inverse. That's just the definition. I mean, literally the same formula. Okay, so A is equivalent to B if and only if there exists X such that A equals X, B, X inverse. And we know very well this definition. This is similar matrices. And it means that there exists bases where basically depending on the choice of a basis, the same linear operator will give you A or B. So then one can look at the set of equivalence classes. And for instance, there is this invariance of equivalence classes. So for instance, let's say determinant of a matrix is a function from a set of equivalence classes to F. Or for instance, trace is a function from the set of equivalence class to f. So determinant and trace are these functions on the set of equivalence classes, and this is very interesting. So we know that this similarity for matrices has meaning that if two linear operators in different bases are represented by A and B, and A and B are similar, it means that sort of geometry of them is the same. Basically, the set of eigenvalues is the same, characteristic polynomial is the same, and so on and so forth. And so this is why this conjugacy classes have some meaning of sort of a geometric shape of your element in a group, and we'll see later why this is the case. Okay, so in the next lecture, I want to talk about symmetric group, and in particular about conjugation in symmetric group and some other related topics.